In this video, we're going to be looking at how the rates of reaction are related to the production of the products and consumption of the reactants. And the reaction that we're going to use as an example in all these slides is the decomposition of NOBr to form nitrogen monoxide and bromine. Now we can express the reaction rate with respect to any of the reactants and products, but we have to be a little bit careful because, as we can see in this example problem, if I make 1 mole of bromine gas, I'm going to be forming 2 moles of nitrogen monoxide. And so when I express the reaction rates, I have to take the stoichiometric coefficients into account. And so in this first problem, we're asked to express the reaction rate with respect to each of the reactants and products. And so to do that, we would say that the rate is equal to, if we consider the NOBr reactant first, to account for the stoichiometry, I have to do the inverse of the stoichiometric coefficient. So the rate is 1/2 the change in the concentration of NOBr with respect to time. Now the other thing I have to do is I have to realize that for the reactants, they're going to be decreasing. For the products, they're going to be increasing. So we like the reaction rates to always come out to be positive. So for the reactants, in addition to multiplying by the inverse of the stoichiometric coefficient, I also have to include a negative sign. So it's minus 1/2 the change in NOBr with respect to time. The products, because they're increasing, their rates will be positive, so I don't need a negative sign. So for the nitrogen monoxide, it'll be positive 1/2 the change in nitrogen monoxide with respect to time. And for the bromine, because its coefficient is 1, I don't need to write anything, so it would be 1/1. So it's just the change in the concentration of Br2 with respect to time. All right, let's go on to the next slide and look at another example. And we're actually going to use this rate expression that we've determined. All right, so I've rewritten the rate expression that we wrote down on the last slide. And now we're given some data about this reaction, and we're asked to calculate the average rate between 0 and 8 seconds. So obviously I'm going to use the NOBr part. So the rate is minus 1/2 times the change in NOBr with respect to time. So let's rewrite that. So if I go ahead and plug in my numbers, I know the rate is minus 1/2 the change in NOBr. Right, I'll go from 8 seconds and subtract from that the 0 seconds concentration. So I have and then denominator, the change in time, I'm going from 8 seconds is the final, 0 seconds is the initial. So when I do the calculation on the numerator, I get negative 0. And then the denominator just comes out to be 8 seconds. So then when I divide that by negative 1/2, I get that the rate is 3.9 times 10 to the minus 4, and the units are molarity divided by seconds. So it's molarity divided by seconds, or molarity seconds to the minus 1. All right, let's look at another example on the next slide. Okay, so we have the same reaction, and we're also going between 0 and 8 seconds. But now I want to know the rate of change of nitrogen monoxide. And so when it asks for the rate of change of reactant or product, what I'm going to be solving for is this whole thing. So I want to know what delta NO delta T is. Now we determined the rate in the last example, so we already know that the rate over this time interval is 3.9 times 10 to the minus 4 molarity seconds to the minus 1. And so I'm going to set now the rate equal to this 1/2 delta NO delta T. So I know that rate is equal to 1/2 change in NO with respect to time. So I can just plug in my numbers. So I know that the rate over this time interval is 3.9 times 10 to the minus 4. All right, so now I just have to multiply by 2, and so I get that the rate of change of NO with respect to time is all right, so this is a pretty easy calculation. The only tricky part is we have to realize that when they ask about the rate of change of a reactant or product, they want the whole thing. They want the change in concentration with respect to time. All right, and we'll do one more example on the next slide. Okay, so now in this problem, same reaction, same time interval, but we're told that the initial concentration of nitrogen monoxide is 0.0050 molar, and we want to know what will its concentration be at 8 seconds. So on the last slide, they asked about the rate of change of the concentration, and so they wanted sort of the whole thing, delta NO delta T. Now, because we're just asking about what is the concentration, now I'm going to be solving for the numerator. So I'm going to be solving for the change in NO. So on the previous slide, we found that the rate of change of NO was 7.8 times 10 to the minus 4 molarity seconds to the minus 1. And so now all I have to do to get the concentration is plug in delta T down here and solve for the change in NO. So I know that the change in NO is going to be 7.8 times 10 to the minus 4 molarity seconds to the minus 1 times the change in time. And the change in time is 8 seconds minus 0 seconds, so it's going to be 8 seconds. So the change in concentration of NO times 8 seconds. So the change in concentration is 6.24 times 10 to the minus 3 molar, right? Because the seconds to the minus 1 cancels with the seconds. Now I'm not quite done yet, because this is the change in concentration of nitrogen monoxide, right? But the initial concentration was not 0, it was 0.0050, so what we need to do is that the change in concentration is equal to the final minus the initial. All right, so we just found the change in concentration. We're given the initial concentration, so now all we have to do is solve for the final concentration. So the final concentration is going to be the initial plus the change. And so 0.0050 plus the change So when I add those together, I get that the final concentration is 0.0112 molar.